All right. Hello, everyone. So I realized I haven't done a pendulum problem. So I'm gonna do one for you now. It's not a pendulum, sorry. Like the rope and ball tension problem, I guess. So this one has a ball tethered to a tall pole and it's thrown around to travel in a horizontal circle. So this is what it would look like, right? You have your pole, you have like a ball, and it's flying around with a V, but you don't know. It doesn't tell you. And then it's making an angle here, 40 degrees. And then has a weight of 0.255 kilograms. On a, and then the rope itself here, I'll put equals in. Rope itself has a length too. And that length is 1.37. Cool. So then it's asking us what's the speed of the ball and what's the tension in the rope. So to do this, we're going to start with obviously our first diagram. So we have our ball. We know we have gravity coming down, straight down. I cannot seem to draw a straight line. What do you mean? Gravity. And then we have our force tension here. Remember, there's no normal force because you're not like resting on anything that's pushing up on you. You do have the X and Y components of this. Right? This is the X. This is the Y. And I'm probably going to use this top side here as theta because that's what you have up here. Right? Let me get rid of this velocity vector. Velocity vector is kind of like going like this way because if you look at it from the top, you had your rope here. So top, your velocity is going this way, even though the motion is going like this, right? Because you constantly have this ft as your centripetal acceleration. So cool. So then we're gonna do the normal force sigma things, right? Oh yeah, y is cosine because it's right next to the angle, and x is sine because it's on the opposite side of the angle. So then we have, I'll put it over here. Sigma of x, which is, you have this x here, so ftx. And you don't really have anything else, but your acceleration is not 0, so that's equal to ma. And seeing how we were traveling in a circle, this means that this x is that centripetal acceleration. So I think she does AR. I use AC. AR is just like radial acceleration because it's along the line of the radius, and centripetal because it's in for the center. It's the same thing. So that's ARC. And then you have, so then that means that t of x of t, yeah, equal to centripetal. So then f of t of x is, I'm just gonna use force as f of t. And then it's the x, so that's sine, the angle, which equals mass. Oh, mass. And then remember that acceleration is same as v squared 2 over r, right? Because AC is equal to, and you know that you're using AC because you have this circular motion. So that means you have centripetal acceleration here. Keep it rotating instead of just flying off. Right, because if you didn't have that AC, this would just go straight out. Okay. So that means you can rearrange, but you don't know force tension yet, right? Let's see here. Let's see. So then you're gonna look to your force of y, or your forces on the y-axis. What you have your Fty in the positive direction, because we're defining this is positive and this is positive. And then you have your Fg, or I guess we're technically defining. Because we're going in a circle, that circular motion doesn't really matter. So it's just into the center is positive. Anyway, on the y-axis, the Fg is negative. And you also don't have any acceleration in that axis because you're just not moving up and down, right? You're moving around. So then that means that Fy, Fg, which means F element space for t. The y is cosine, so cosine theta equals to mg. And then you can divide both sides. This is a t. By both sides. By cosine theta. Right? So then let's do this in blue. We can cancel these out. And that gives you two equations. This one and this one, which you're going to plug into each other as soon as I draw them. And then you have your FT. I'm gonna plug this in here and do that in blue. I'm just gonna put this m out here. This is acceleration. Note that these two cancel out because they're both m. This becomes tangent theta. I guess we could do the whole multiply thing because we're gonna need to get rid of this r anyway. So this r gets rid of. And then that becomes r g and theta is equal to v squared. And you're just gonna square root both sides, right? Oops. You're gonna get rid of that squared on the v side. And then you're gonna plug it in. So I'm gonna go v is equal to the square root of whatever I text. So r is, oh, you need to figure out r? Single rope thrown at a 40-degree angle. Hmm. Oh, okay. We need one more thing. I guess while I'm already drawing stuff, might as well. The reason this is the same as tan theta is because you have sine over cosine. Aside from knowing that that's one of the definitions of tangent. You have sine over cosine. Sine is opposite over hypotenuse, right? SOHCAHTOA. And then cosine is adjacent over hypotenuse. So that becomes opposite times hypotenuse over adjacent times hypotenuse. Hypotenuses cancel out, so that equals opposite over adjacent, which is TOA, right? Get that from, so uh so cool. I think we're also looking at angles here. We have R here. R here. That's on the sine side of this 40 degrees, right? Equals. So we'll do sine theta. So go to the opposite. In this case, we're looking at the actual values of the lengths. Here we're looking at forces, right? So it's for forces. It's for lengths. So the sine is opposite over adjacent. That's R over L. So that means that R is equal to L sine theta into capital. So to bring that on over here, we have our R is equal to L sine theta. We can go ahead and plug that in there. So that is equal to Now you square root are saying L sine theta G tan theta. I obviously drew that too big. And then you're gonna plug in. And you get L, just 1.37 meters, and sine 40 degrees times 10 gravity. Six, nope. Yeah, 9.8. You know, that's second squared times tangent 40. Yes, I recognize it's kind of cutting into other stuff. I will remove it. This is- And that means that V is equal to, go ahead and plug it in. I got 2.69 meters per second. So then that's A. Oh, I guess I could, yeah, I'll do the 2.69. And then it asks for the tension of the earth. Then, you know, from our previous drawings over here, force tension it's mg over cosine theta. So then you just plug them both in. You do have your mass that gives you that. Gravity 9.8. Go ahead and plug that in. I got 3.26. That two is badly going. Newtons, right? Because you have kilograms, meters, seconds squared. Oops. And that's your force, so you expect that. That's your B value. And that's the problem. Well, much easier than the pendulum problem that Dr. Bradley was trying to get us to do. Copy and paste that. That was from one of your practice problems, so. I also have a force on the box problem. Because I feel like this one is really good for force friction. So right, you already have them all drawn out. You have your force pushing in here. You have your normal force replying to that, and those are equal. So then sigma x equals to, if you need to pick an axis, I'm going to pick the normal one that I usually use. So then that means that force push is regular. We'll put a P here. And then if normal force is negative, and then you're not going to be moving in this direction, right? The wall is going to meet you however far hard you push. So then that gives you the equation that force push equals normal force. And then you do that for the y. Here you have force friction going in the positive direction. I just use force F. This usually like the squiggly F, but I'm a little trouble drawing it here. And then you have force gravity. Right? You want this to be 0. So 0. I'm gonna put a little note as to why. Right? You want it to not fall. So that means that your y acceleration is going to be equal to 0. And that little equation gives you force friction is equal to force gravity at minimum, right? It could definitely go like larger if your force push was larger, but at minimum, when this is 0. Note that your force friction is always going to oppose motion. So even if you did increase your push, there's no motion, so the force friction would not be all that affected. Now you have to remember that the definition of force friction is mu times the normal force, right? So I'll write that in green. This becomes mu times the normal force. And that's just something you need to know. Memorize that equation. Much how this one is always mg, right? So then that means that this force M can come and get plugged in here. And that gives you mg is equal to mu times force push. Okay. So then you're actually solving force push, right? These here are for force push. So then it would be beneficial to isolate force push. So divide by mu. That gives you force push equal to okay. Sorry about that. Okay. Anyway, I totally forgot to pause that. Oh well. 20 newtons divided by mu g 0.4 b. And that gave me that line is way too long. It's 50 newtons. And that's the minimum force. So that means that your answer here would be C. Cool. Go ahead and clear these. And I got these from your in-class exercise. Okay. Now this one might take a while. Heads up. So there's a few ways of imagining this first off. You have a car. It's entering a rounded flat curve. The key word here is flat. I always felt like the point of this one was to show you that like how much the banking of the curve really matters. So anyway, so you have this car on a curve. I'll do it over here. It's coming on the curve. This is your car. Imagine it's a car. You have an arm. You have a radius for that curve, which is 40 meters. This car is going tangentially, technically, right? Just technically going on a tangent, but you're just gonna draw it a little straight. a second. And then I guess you could also put that the mass is that much. Okay. So now you can also imagine the car just straight on the road. Just the road, that's the car, just stop. Let me at least try and make it work. Okay. On the side, you have your gravity, right? And you have your normal force. At the top, you have like a little bit of a pull in here, right? You assume that this is towards the inside of the curve. I'll draw it like this. And here's gonna be force friction. It's exposing the motion or going in. And this is your centripetal acceleration. Actually, no. You only have force friction here. And the reason for that is because centripetal acceleration is not a real force. Hello. Oh my gosh. There we go. Okay. It must come from, sorry about that. Oh, yes. In this case, it's coming from force friction. And in the swing one that we did, where we swung it around in a circle, it was coming from the force tension. Okay. So, and then you go ahead and do your sigma forces. Do y first. Okay. Oh yeah, I need it to my axis. Positive, positive. This is gonna be 0 because there's like flat, right? And then this next one, you want it to be 0, but you don't know that it is. Because it's asking you if it will skid. Note that this is MAC because you're going into the circle or into the central. So it's centripetal acceleration. So that means it's equal to m to the v squared over r. Because AC is equal to v squared over r. Right. So then this equation here becomes force normal equals to mg. Right, because FG is going to come to the other side and become mg. And then this one's going to become force friction, which, all right, blue. So then that's going to become n times mu Fn is equal to mv squared over r. So then you're going to plug Fn there. So then blue. And you're kind of combining these two. Into mu and right, and then you're gonna divide, like, because you know those ends are gonna cancel out. Now's a good time to pause, look at what it's asking for us. It's asking, will the car follow the curve or will it skid? Well, we actually have all of these. It's given, m is given, mu is given, gravity is known, m is again given, velocity is given, and r is given. So what are we solving for? The question here is, will the car skid? So for that, we need to know what the mu s, or like the static coefficient of friction necessary is. So let me put that in a little note. I'm just gonna use u. Right? So we're gonna isolate u or mu, because everything is given, but you don't know if the car will skid. So you need the minimum mu because you're given two. You're given one here. Then blue here. And you're given one here. So you need to use that to compare. Okay. So then that means that this is gonna go ahead and become mu is equal to, I'll write it, mv squared over r over mg. These to cancel out. This one's gonna kind of multiply up here. You can kind of imagine that's over one, so then those bracket up. So that's the same as e squared over gr. And you can plug in for that. V is 18 meters per second squared. GR is and you have your radius, which is 40 meters. Note that that's going to be meters or seconds. Like it's their units are going to cancel out basically. If we plug that in, I got 0.83. All right, let's meters seconds squared. Well, that's fine that there's no units. Right. So then you compare that. So this is actually bigger than both of the mu's given. And then you look at those, you're like, oh, that's less than 0.83. That's also less than 0.83. The car skids. Either way. It's kind of scary. But then if you bank it, then you're a lot less likely to skid. So that's over here. And then I'll draw. I think she did an example problem. Something like this. I have it in here in my notes. Okay. It's also like example 5-4 in the chapter 5 slides. But I think there she just kind of did the F is equal to MAR. That's what's required. So she kind of just looked at the force needed for acceleration, yeah. She kind of just looked at the force friction is equal to mass times acceleration. And then solved for like what MGU would make that like force the same as the required force. And they were both smaller. I'm gonna do a little tangent. If it's banked, then you have like this. Have data here, your car here. I know that's a really steep bank, but there you go. So then here you have MG, have your normal force, helping. And then theoretically, if this was banked enough, normal force could replace force friction. And normal force is a lot more likely to keep you from skidding. So then you're less likely to skid off the tracks. Well, and I do believe that was all from me today. So, yeah. I hope you guys have a nice day and take care.